Why study energy? Why have such a thing as energy? Well, obviously, energy seems to be an important thing in society, right? Uh, Eventually, energy is related to things like heat, energy stored in coal, and etc. But for the time being, let's go back up. Why do we need a concept of energy? Well, we find out some of the problems that we were doing. Remember problems like we were doing just now? Uh, could be done a lot more easier if you use energy concepts as opposed to using Newton's laws. Newton's laws become difficult or sometimes impossible to use, but energy is much easier. For one reason, energy is not a vector. If it's not a vector, that's good news. That means it's going to be simpler to use. It's a scalar, so it's a number. It has no direction associated with it. Now, the number could be positive or negative, but basically there's no direction associated with energy. Energy is like time. It's like a fundamental concept, like space and time. There's no good simple answer to what is energy, like if there is, as there is no good simple answer to what is time, is what is space. We have sort of feeling what they are, but it's kind of harder to actually put a definition into it. But there are some things we can say about energy. Energy, we're going to see. The first thing, energy in its definition, is the ability to do work. If something has the ability to do work, it has energy. Now that energy can be stored, and it also can be changed from one form to another, like thermal energy, mechanical energy to thermal energy, gravitational potential energy, and either kinetic energy. These are the things, some of the things we're going to look at in this chapter. What are we talking about when we say all these things? First of all, we'll start with what is work. It is the ability to do work, but what is work? Well, here's work. If you apply a force, like this young lady is applying it to this box, and as a result of that force, let's say the force is 75 newtons, it pushes the box a certain distance d. Work is defined as the force times the distance that it pushes. To be specific, later on I'm going to say it's the displacement, but right now let's assume it's just the distance. For example, if she pushes it with 75 newtons of force and moves it to a distance of 10 meters, then the work that she did is force times distance, which is 75 newtons, multiplied by 10 meters. So how much is that? Well, that's 750. But what are the units of that? Well, they're called Newton meters. So 150 Newton meters. Very often, if we have a lot of different words for a unit, we sort of replace it with a different word. Like one word that replaces these two Newton meters, and that word is a joule. A Newton meter is a joule. So instead of writing 750 Newton meters, we say 750 joules of work was done. This is after James Joule, who was a brewer, by the way, and also a physicist. But he was an inventor. Okay, so in his honor, they call this unit a joule. So work equals force times distance, but what if the force, we did a simple problem where the force is in the same direction as the displacement. But what if the force is at an angle? You either push at an angle or pull at an angle. Well, if the force is at an angle, then obviously it has two components, which can be replaced. That means two things are happening. The object is moving to the right, and there is a force to the right, and there's a force that's perpendicular to the direction of motion. Don't forget, the direction of motion is to the right. Oops. Direction of motion is to the right. And one of the forces is perpendicular to that, and the other one is parallel to that. Okay, let me put them up here. This is parallel, this is perpendicular to the motion, and this is parallel to the motion. Don't forget, these are the components of the original force. Now, if you, instead of pulling, you're pushing, it's the same thing. There's going to be, except there'll be an opposite direction, there'll be two components of that force. That will replace this force F that I have here. Turns out that only the X component contributes to work done in this equation. The Y component does not. So basically what we're saying then, the work done is equal to just the X component, or the component in the direction of motion, which, going back here, right, this is an angle theta, this is the force, this is theta. Basically the work done would be F, not times D, but D cosine of theta, because only this component of that force does work, and that component is F cosine theta. So if you push down on a box, straight down, like this guy's doing, you do no work. Or if you push straight up, like you hold the box up in your hands, you do no work. Because you must, first of all, you must have a displacement. If that angle is 90 degrees, then the equation tells you cosine of 90 is 0, that you do no work. So we can say this: the work done by a force is equal to force times the displacement in the direction that's parallel to the displacement, in the same, that part of the force that's parallel to the displacement. And again, the units for work is Newton meters. Don't forget, a Newton is a kilogram meter per second squared. That's what a Newton is. So in reality, a joule, which is a Newton meter, is also a kilogram meter squared per second squared. Luckily, we have one word that replaces all those words: joule. Okay. So right over here, we see 1 joule is 1 Newton meter, or 1 kilogram meter per second squared. So as I mentioned before, work is not a vector, it's a scalar, but it is a multiplication of two vectors. Force is a vector, and displacement is a vector. But work is not a vector, it's a scalar. It can be positive or negative. Work is negative if the applied force is the applied force is supposed to be, work is positive if the applied force is in the direction of displacement. Over here, positive work. Work is negative if it's opposite to displacement. In other words, if something is moving this way, but a force acting on it is that way, that force does negative work. Okay? That's only possible if there's another force acting on it. So basically right here, if a force acts in the same direction as the object motion, it does work, positive work. If it acts in the opposite direction to the object's motion, then it's negative work. If the object does not move at all, then there's no work at all. Zero work is done. And we're going to look at some examples of this. So, for example, let's say you're holding a ball and you're just holding it. So that means you're applying a force up to keep it here. But you're not moving it. There's no displacement. So even though you may be getting tired holding this bowling ball, but you're not doing any work. By the way we define work, you're not doing any work. If, however, you push the ball that way, you can just walk that way. It means you got to apply force this way. You are doing work, force times distance. And if you're moving the ball to the side, like sideways, then only the component of the force in the direction of motion, forget this is the direction of motion, only the component of the force in that direction does work. So here's another example of this young fellow is holding a box, pretty heavy box. He's getting pretty tired. He's applying a force up, but there is a force down, but he's not moving it up or down. But let's say the box is on the floor, and he now applies the force up, and force applied, and also there's a force down equal to mg. Don't forget, work is done by forces. So this force up does work. How much work does it do? mgh, force times this distance. Let's say he lifts this up very slowly, a constant speed, so there's no acceleration. All right? There's no acceleration means F is equal to mg. And therefore, the work he does is F times h. H is the height that you lifted it. So if you lift something, say put it on a table, you lift to the height of h, this is how much work you did. You did this work against gravity. Gravity was trying to oppose you. But gravity did, as you were lifting this, gravity did negative work. Why negative? Because gravity is down and the displacement is up. So gravity does negative work in this case. So you have work done by the force F. That means the force exerted by you. And you have the work done by gravity. This is mgh. This is minus mgh. For example, say you lift a 7-kilogram mass at a constant speed, a distance of 1 meter. 1 meter. So delta x equals 1 meter. Okay. And this is mg, which in this case would be 7 times 10, or the force up would be 70 newtons. So the work that you do, this force does, is going to be 70 times, or if you for G, if you use 9.8, it'll be mg, mass times 9.8 times 1, it'll be 69 Newton meters or 69 joules. That's how much work you do to say to lift this up and put it on a table, this box. If the table is 1 meter off the ground, you've done 69 joules of work. So here is a little multiple choice question. And in order to do that, I need to go over here. All right. A horizontal book slides 2 meters. This is 2 meters. Across a horizontal table with a friction force of 3 newtons. In other words, there's a force this way, the object is moving that way. So friction will be opposite the direction. And let's say the force of friction is 3 newtons. So the question is, how much work does the force of friction do if the book slides 2 meters? How many joules of work? So I'll give you a hint. Nobody seems to know the answer. Work is force times distance. Well, a couple people said D. D is not the correct answer. Yes, E is the correct answer. Why? Force is moving this way. I'm sorry, the box is moving this way. The force is opposite direction of motion. And we said in those cases, work is force times distance, but it's negative work. So the amount of work the force of friction does is minus 6 joules. Okay, now there could be somebody pulling this way with a force of 3 newtons. Then they do, yes, plus 6 joules of work, this force. But we're talking about friction. It's doing negative work. This is what negative work means. All right, machines. We'll talk a little bit about one application of energy is various machines. First of all, a question. Some of you guys, maybe some girls also have been working out, during the pandemic, doing weights. So you get strong enough. Can you now lift a car? What do you think? Can you lift a car? Well, if you've ever changed a tire, you've lifted a car. Well, maybe not everybody has changed the tire, but many of you had, right? And you did lift the car, and you did not necessarily need to work out with weights. So how does that happen that you can lift a car? This is how it happens. A car jack is an example of a machine. This is what happens. You have a jack. Jack works on this principle. Okay? You apply a force over here, and you move it to a big distance. The amount of work you do is going to be that force, a little force, times this big distance. Okay, you can see the little force here times this big distance. As a result of that, what happens? There's a force that actually lifts the car up. It's a big force because it actually applies a force. Well, if the car's on the ground, it's not the weight of the car, but it's part of that weight, a good part of that weight. But the distance it rises up is a tiny distance. You got to do this like 20 times to get the car high enough so you can take the tire off. Because each time it's like a centimeter, maybe less than a centimeter. Tiny distance, and up to 20 times it actually comes up, a couple of inches off the ground, and you can take the tire off. But the work you do is this force times that distance. This is a big force times a little distance, and this is a little force times the big distance. But the work done has to be the same. Okay, the energy that you expend here has to be the same, equal to the energy that is expended in lifting the car. Okay, so a little force times a big distance equals a big force times a little distance. For example, the car could weigh 5,000 newtons. All right, so you're going to need about 5,000 newtons to lift it up. But you can only apply 50 newtons. But 50 newtons, let's say, I'm just making these numbers up, is a quarter of a centimeter. It's supposed to be 0.25 centimeters. Very tiny distance, quarter. But you can do this many times, all right? Sorry, not, yeah. But they're using over here just 25 centimeters. So 50 times 25 has to equal on this side, this big force, 5,000, times a tiny distance, 0.25. Okay? So this times that has to equal this with a big F, a little d. Here you have a little f, a big D. Bigger in comparison to this side here. Now, the ratio of the input force to the output force is called the mechanical advantage. The ratio of these two forces. The mechanical advantage here is 5,000 divided of this jack. This is the mechanical advantage of this machine called the jack. And this is 100. That's a big mechanical advantage. Okay. The mechanical advantage of this jack is 100. You can see it over here. Let me give you another example. So let's say we have a 2-pound bag of potatoes. Oh, this is potatoes. This is sugar. Bag of sugar. 2 pounds is about 9 newtons. All right. So you would say, well, I need to lift this up. I need to apply a force up of 2 pounds or 9 newtons. But I say you can lift it with less than that if you are smart, if you take physics, right? So this is, let's take a look at this situation. So let's say you're going to pull this up over this pulley. There's a force of T, let's call it T, tension in the string, and there's a weight down. Now, if you pull this very slowly, you don't accelerate it up, that means T is equal to mg. And basically, the pull that you are pulling with is T also. It's a tension in the string. So in order to lift this up, you need to apply the weight, because T is equal to mg, which in this case would be 2 or 9. But think about this one. You're smart. So you apply a force of T over here. This is what you're pulling up with. If you had a scale like this, this would be the reading of the scale. And the string goes around, and there's another force on the other side, also T. Of course, down you have mg. So all the forces up, you're doing this very slowly, no acceleration. All the forces up have to equal all the forces down. What's up? T and T, 2T. What's down? mg. So what's the tension in the string? Half the weight, that's right. mg over 2. So basically, if this weighs 2 pounds, you can pull it up with 1 pound by applying a force of 1 pound up. If you have a pulley that helps you like this. How about, so this is basically what it would read. If this was 2 pounds, if you put a scale here, okay, it would read 1 pound. Or if you're using newtons, it'll read 4.5 newtons. Generally speaking, and I still remember this from when I was a child, I'll tell you the story in a second. You say you have a system of pulleys. There are many strings here. What happens is that the weight of this object is distributed among all the strings. And you are holding just one of those strings. So the force that you'll be applying to lift this object is going to be a lot less than 500. Okay? But in order to lift this up, you got to pull down. Here, you're going to pull down a long distance, pretty long distance. This is the big D here on the left side, big D. But as a result of this, this thing is going to rise a tiny distance. This is tiny d. So you're going to pull down a big distance. This thing goes up just a little bit. That's like the jack, remember? So let me show you this also in a little simulation. So this young lady is going to lift very slowly. She's going to lift very slowly a 250 Newton weight. So right now, obviously, I can control how much weight she needs to add. We know that she's going to need to exert about 250, and actually to have it go up with 251, I'm going to set it at. Let's see. You can see it going up a little bit down here, right? Very slowly, very slowly. She basically has to exert the same amount of weight as this is. But let's reset this and have a different pulley system. How about this? Don't forget, this weight, 250, is now distributed among these two strings. She's holding one of those two strings. All right? So this should be just split up equally among these two. That means she shouldn't need that much, probably half of that. Let's see. So that half of that would be 121. Let's make it 126 so actually it goes up. Yep, she's able to lift it. You can see that here. With half the weight, she's applying half the weight. All right, 126 newtons. We can be even more trickier. How about this? Now, the weight of this is split up among three strings. And she's holding just one of those three. Each string holds a third of this. So 250 divided by 3 is equal to 83.3. That means she should be able to lift it by 84 newtons. Let's see, I'm going to put this down, 84. And let's hoist it up. $84 newtons. Now we have four strings holding it up. So therefore, 250 divided by 4, she should 63 newtons. She should lift it up. So the story that I want to tell you is this. When I was a child, I lived in Manhattan, and some movers came in. They were going to deliver a piano to like the 4th floor. And the way they did it, you couldn't carry it up the stairs to the 4th floor. They had a system of pulleys on the roof, and they hoisted the piano up, and they brought it into the apartment through the window. Okay, and basically one guy just pulling the piano up. Then you needed two guys to get it into the window and put it on the floor. So let's look at these pulley systems. So for example, this is the one that we sort of spoke about. If this is W, then you have 2T up, T and T, and therefore each tension is half the weight, because 2T up, weight down, each tension is half the weight. Over here, if you look at this one here, again, the tension here is going to be split up among the 4 strings, so each one gets 1/4 the weight. Let's do a little problem here. Let's do this one here. So if you want to lift a 500 Newton weight, a distance of 10 centimeters of 0.1 meter, how much force will we need to use, and through what distance will we move? All right, so basically this force here that you apply times this distance it moves has to equal this force here, which is the weight of the object, times the little tiny distance it moves over here, little d. Okay, this is bigger d. So the right side is T, or T is tension in the string. TD equals, this is F here, times, this is what they call H. Okay, this force times this distance, H, is equal to this force times this distance, D. or the work done here has to equal the work done there. And if F, the weight is equal to this force here is equal to 500, right? T is be 1/2 of that over here because it's split up. So T times D times F, D times 250 is equal to the weight times the distance is high, it rises. So basically, it'll move up 0.2 meters. Not it'll move up. You will have to move 0.2 meters to get this up, just 1.1 meter up. The mechanical advantage of this is 2, all right? Mechanical advantage is just the ratio of the force that you apply here to the force here, which is the weight. Let's see if we can do this. The effort required to lift a 10 Newton weight is how much? How much force will you need to pull? And then we'll do one more part to the same problem. This is 10 newtons. The question is, how many newtons is this? This 10 newtons is split up among how many strings? Because you're holding just one of those strings. Can't figure out how much, what the force is? People can't figure this out? Come on, I know you can figure it out. It's 10 newtons, and you're holding 1/3 of that. So how many newtons are you holding here? That's right. B is the right answer. All right. So there's another part to this. One more part. If I pull down, this is me. I'm pulling down here. This distance, 9 meters. How much does this go up? I'll give you a little hint. I'm pulling down here with some force. We just figured out how much force that is, the previous question. So the work done on the left side by me here, F times this D, is equal to the work on the right. Don't forget, on the work on the right, this is the weight of this thing is moving up. It's going to be the weight times, let's call this distance X. I want to do a different color, X. What is X? F times D. Don't forget what F is. We calculated it. It was 3.3. That's what F is, 3.3. D is 9. Okay. The weight of this thing was 10, if you remember. Force times this distance equals this force times that distance. So X equals this time this is 29.7 divided by 10. Doesn't seem to be the right answer here, right? I guess it should be so basically it should be that you are weight will rise a distance of should be 3 meters, right? So they round this off. I guess they rounded it off. 3 meters. It's 2.97, right?
Yeah, and they just rounded.
Let me write it this way, about 3 meters. All right, so we're going to stop at this point and continue on with work and energy on Wednesday.
It's due on the 22nd, I believe.
What's due on the 25th?
Chapter 4
I'm sorry.
due on March 22nd.
Yes. When is the chapter? You're talking about the Weber-Stein homework, right? Chapter 4. Right, it's due a week from Sunday, the previous Sunday. No, was it the 25th, did I say? I think this coming Sunday. Chapter 4 Weber-Stein homework, because we just finished chapter 4 today. Maybe I forgot to put it in this Sunday, the Sunday after. And there is a alternative homework on Blackboard, yes. It's still unavailable, but I'll make it available right now.